Hello everybody, I'm Lorenzo Maffi, and today I will talk about the self-dual critical theory on the surface of topological insulators. This presentation is based on this paper written by me, my PhD supervisor Andrea Cappelli, and PhD student Francesco Andreucci. We all know that the low-energy behavior of a physical system is well characterized by its own symmetries, and the standard way to think about a transition between two different phases is the Landau-Ginzburg theory. We define a local order parameter which allows us to distinguish the symmetric ground state from the gapless ground state which spontaneously breaks the symmetry. However, in the early 80s, we discovered condensed matter systems realizing quantum phases not explained by local order parameter, which are known as topological states of matter. They are characterized by global effects, and they have gapped non-trivial ground state, where non-trivial means that we have measurable low energy features for massive excitations, such as exchange statistics, and the ground state is degenerate on space with non-trivial topology. In addition, we get gapless edge modes when the topological state is defined on the manifold with boundaries. All previous universal properties can be captured by topological effective gauge theories, where topological means that the action does not depend on the metric, so the Hamiltonian is null, while the gauge fields are interpreted as the hydrodynamic fields effectively describing the conserved currents in the system. For instance, in 2+1 dimensions, a conserved matter current can be written as dual to some one-form gauge field. In addition, if the system is defined on manifold with boundaries, the topological action is no more gauge invariant, and so we need the bosonic massless degrees of freedom located at the edge. These bosonic massless degrees of freedom are described by conformal field theory, whose variation under the gauge transformation cancels the variation of the topological bulk action. Now, let me briefly introduce how these tools work in the case of the time reversal topological insulators in 3+1 dimensions, the so-called topological class A2. In the non-interacting case, the topological insulators are described by fermion bands with level crossing located on the surface. This leads to a boundary 2+1 dimensional massless fermion, and once coupling it to an external electromagnetic field, capital A, we get the induced action on the surface, which is made up of a time reversal breaking term plus a non-local term at the quadratic order in the external field. The time reversal breaking term is cancelled by the bulk effective action, which is the well-known theta term with a theta equal to pi, and so we have just the non-local term at the quadratic order in the external field. On the other hand, in the interacting case, we are forced to get rid of the macroscopic theory, and we are led to use the topological effective theory. The topological effective theory is a topological BF theory for our case, with topological invariant K, and when K is equal to 1, we get the bulk theta term for the effective action, while when K is more than 1, we get a fractional generalization of it. We know that the gauge invariance requires a surface term that looks like that. We have a BF term for two hydrodynamic fields arising from the bulk, zeta and little a, and electromagnetic coupling. These terms are topological, so their Hamiltonian is null, and we need to add a conformal dynamics. We need a conformal dynamics on the surface. We propose the so-called loop model, which is essentially a no-local interaction between conserved matter current in 2+1 dimensions. We choose it in order to reproduce the non-local induced action previously seen in the case of the 2+1 dimensional free fermion. This non-local theory on the surface, called the loop model, has many interesting features. It gives us the same non-local inducible action of the fermionic theory for k equal to 1, and as I just said. And it possesses a critical line as the chiral boson in 1 plus 1 dimensions, and this suggests some connection between the chiral boson in 1 plus 1 dimension and the loop model in 2 plus 1 dimensions. In addition, it is a self-dual with the G in 1 over G under the duality web transformation in 2 plus 1 dimensions. However, the spectrum and the partition function haven't been calculated yet. So we evaluated the partition function for two spatial surfaces, a spatial torus T2 and a spatial sphere S2. In this talk, I will present just the result for the sphere case. However, we have a problem because the action is non-local. It contains infinite derivatives in time. So there isn't any viable canonical quantization approach to resolve the problem. But the theory corresponds to a local theory in one or more dimensions, and this is the key for us to resolve the problem. Indeed, the Son et al. Proposed a mixed quantum electrodynamics with the photons living in a 4D space-time and fermions living on a 3D embedded brane. This theory, once we integrate the photons out, gives us the loop model interaction between the fermionic currents on the brane. So our strategy is the following. We consider the 4D local version of the loop model by adding to the BF term arising from the bulk a four-dimensional Maxwell term that once we integrate the Maxwell term out, gives us the loop model on the brane. So this 3D brane corresponds to our physical surface. Then we decompose the fields in solitonic and oscillators modes, where the solitonic modes satisfy the boundary condition fixed by the bulk boundary correspondence, which are essentially two magnetic fluxes for the two hydrodynamic fields. Then we get the oscillators modes contribution from Lagrangian approach by a zeta functional regularization. The results on a spatial sphere are particularly interesting, very interesting, because the cylinder can be mapped to a flat space via conformal transformation, which maps the Hamiltonian of the theory on the cylinder with the dilatation operator to the dilatation operator of the theory on the space. So we can directly read from the partition function the conformal dimensions of our conformal theory that fully describe the observables of our theory. The solitonic partition function is the sum over the solitonic charges. Note the free parameter lambda that enters as non-universal Fermi velocity, and note the manifest self-duality G0 in 1 over G0 that exchanges the electric charge with a magnetic charge. In addition, the oscillator part confirms the conformal invariance of our theory. Indeed, the Casimir is 0, and we have integer space dimensions of descendant fields. Note that the spectrum of the descendants is integer as in 3 plus 1 dimensional theories, but the multiplicities are linear as in 2 plus 1 dimensions. So the loop model can be viewed as constrained Maxwell theory enjoying a subspace of its Hilbert space. Now let's move on the conclusions. The loop model gives us the critical theory on the surface of a 3 plus 1 dimensional topological insulators. It provides an example of a non-trivial conformal field theory in 2 plus 1 dimensions, and it has some similarities with the chiral boson in 1 plus 1 dimensions. Indeed, it possesses a critical line as well. And it admits a local theory formulation in 3 plus 1 dimensions that allows us to check the conformal invariance and the self-duality for partition function on the cylinder. And finally, it provides a viable approach towards the 2 plus 1 dimensional bosonization of free and interacting fermions, as the chiral boson do for in 1+1 dimensions. Future perspectives are the following. We will explore the other dualities of the loop model in presence of a Chern-Simons term, and we will extend the analysis of order disorder fields in 2+1 dimensions in order to get a viable approach towards the 2+1 dimensional bosonization. And that's all. Thank you for your attention.